This is a project demonstration video for the project entitled Monitoring and Detecting Malicious IoT Network Traffic Using Machine Learning Techniques by Charlie Steptoe. Internet of Things networks typically include many devices, all performing very different functions and producing very different traffic. Unfortunately, many of these devices are badly configured and susceptible to simple cyber attacks. Cybercriminals or script kiddies may wish to use these devices in botnets for their own personal use. These hijacked nodes will very often call out to their attackers, but it can be difficult to tell this traffic from the very noisy standard network traffic. So, what can we use to tell these anomalous node traffic from all the normal traffic? The two primary methods for this are to use autoencoders and clustering. Proposed as recently as 2019 in Shahid et al., autoencoding neural networks can be used to identify anomalies in network traffic. These networks are trained on a large volume of standard network traffic until it is able to reconstruct the traffic nearly perfectly. When we train the network too well, we find that when given some slightly different input, it isn't able to reproduce the traffic as well. This is known as overfitting, and this disparity is how we tell anomalies from normal devices. With this reconstruction error, we can define any traffic with a value below a threshold as being expected, and any with values above as being anomalous. In clustering, data points are collected into groups with a corresponding central mean. To tell anomalous data in this case, we must use the distance to the nearest mean in place of the reconstruction error discussed previously. Clustering can also be very useful for classifying any network traffic. Using all the cluster means, we can identify which mean a point is closest to, and so determine which other points this data is similar to. We then label this data and relay this information to the user. In the project system, input traffic is passed to an autoencoder, separating it into standard traffic, which it passes on to a clustering classification, and anomalous traffic, which can produce alerts to the user. Labeled traffic is then given to the think tank of the system, relearning. This system produces a dataset on which to retrain the autoencoder in clusters, so as to learn about the anomalies and not alert again. These systems require a very large amount of data for training. Thankfully, an IoT traffic dataset has been produced over 20 days by UNSW Sydney, including IP cameras, smart bulbs, and more. In total, this dataset contains over 165,000 DNS requests. Sadly, this volume is still fairly small for training and testing, so, using a technique known as few-shot generation, each device's requests were scaled up in the used data. To simulate anomalous traffic, patterns of multiple devices were combined, producing a new, unknown device. In total, the generation test data contained 20 sets of 800,000 requests each. Every 2 of these sets, a new anomalous device was added, up to 10 anomalous devices in the network. Let's see the system in action. So here we are in IntelliJ, and we're going to use the full system with some default parameters as highlighted here. Starting the system off, we can instantly see the standard traffic being transformed into its vector embeddings, and then being used to form the clusters for classification later. Next, we see the autoencoder initializing through Deep Learning for Java library and beginning to train. This can take a while, so skipping forward, we see the autoencoder has finished training and has begun classifying anomalous traffic, as can be shown here by MAC address. Anomaly data is then finished, and then the necessary data exported to a file. An important note is the system has already identified the artificial anomaly present in the dataset. Classification statistics are also exported. Retraining can then start on the new data. To evaluate the system's performance, we compare it against the clustering-only technique suggested earlier, with our system's anomalies detected plotted on the bottom graph. Note that due to relearning, we should expect both systems to only have values above 0 on odd datasets, and at this point, we expect the value to be 1. Iterating through the datasets, we can observe the occasional deviation from the expected plot on both systems, but with the clustering algorithm deviating more than our own. Ultimately, the clustering-only system behaves unexpectedly on 5 out of 20 sets, and our own only 2. We can quantify this using mean squared error, where the opposing system manages an error of 0.25, whereas our own has a total error of only 0.028, representing a nearly 10-fold improvement on more traditional methods. Thank you for listening to this demonstration video.